So you can start.
We can start. Okay. Okay. Good. So we have some demonstrations. Some of these Shoda will take you through. So first of all, I have to tell that we are the team from IIT Hyderabad. Very sorry we could not participate live. Means I was not physically present there because of some extenuating circumstance at home. However, I hope you all enjoyed the workshop who are there physically and had a great time. So I hope to have such time in near future. So the point that I want to say is that in MicroSim you have heard a lot of talks. You have heard the general festival approach from Guru. You have heard about the grand potential models, the details, and um, from Avik. And then Funny has also gone through several stuff. So now Mohan and Funny, they have developed this OpenCL, which is also a GPU version. So here we are basically developing the another GPU version of the code. So GPU module, GPU based module, which is CUDA module. CUDA is NVIDIA CUDA. So it is proprietary, although it's proprietary of NVIDIA, but it is CUDA is given as open source, and it has all open source libraries like CU50MP and stuff. And we will show you how using CUDA you can basically write codes and accelerate them, and apparently you can do all the simulations that have been done on multiple CPUs. Although we do not have as many GPUs as we would like to have currently in the supercomputing machines. However, we have done scaling studies also up to 16 GPUs. We could not go beyond 16 GPUs, although we have bottom city. There is some small issue that is coming up regarding some of the Docker and stuff. So this we will resolve soon. But again, we are now basically stuck with 16 GPUs. We can't go more than that. So that is something that I have to tell you. Means when we did the computation. But remember, one very important thing about GPUs, I think Funny also might have told you, that CPUs, obviously you will see sometimes the larger the number of CPUs, you have seen the way the GPU models and many codes have been developed. You could see that you can really get very good speed up. So, but here please try to understand that here also you get some sort of a portability. So if you have the means a laptop, means standard laptop where I'll present all my demo, and if you have a good GPU, you can still run some of these things. So basically, as I told you, so instead of GP model, although we are planning in future to release the GP also, the CUDA version of the GP models also, but this is where we have adapted the KK's formulation, the Kim-Suzuki formulation of the physical equations. And it is like multi-phase. We can handle multi-phase. We can handle multi-component. The multi-grain the active parameter tracking is on the way. It has not yet come. It will come in the next release. And we can simulate precipitation. We can simulate solidification. In precipitation, we can take into account elastic space effects. And as I told you, computation is on the NVIDIA GPUs. So I'll just see here. So I can use this. Yeah, this will remain as a permanent marker. So I'm really sorry. But anyway, it's okay. So you have NVIDIA GPUs, and we use CUDA platform. And you see so we have multiple GPUs. We can use, our code can use multiple GPUs using MPI. And this MPI is called CUDA aware MPI. So basically, this means these are like GPU aware MPI. So that means you can communicate directly between the GPUs. You do not require to go through the via the CPUs. Anyway, Shoda will interrupt me if I am telling anything technically wrong, because Shoda is one of the guys apart who has implemented this multi GPU code, and he's like the technical expert in terms of multiple GPUs. So. Now, so we have done one very important integration here. We have used CUFFT-MP. So CUFFT was originally there by NVIDIA used to provide and it was open source, built on FFTW, and CUFFT basically was for a single GPU. Then it also had some CUFFT XT, I think, right? So which basically, yeah, so which basically had multiple GPU capability, but that also on the same board. But then CUFFT MP, hello, is there any? Okay, so CUFFT MP basically helps you. Is anybody asking?
No, nobody's asking.
Okay, so CUFFT MP, you can use multiple processors, and you can also use multiple GPUs. So it enables rapid elastic calculations. Again, the rapid with restriction of 16 GPUs. We can apparently go further, and we can make. We are also working on how further we can optimize the solvers. So, but we are limited to 16 GPUs. Remember. So, and also the visualization, you can do paraview visualization is there, HDF5 file writing and HDF5 and VTK file writing. All of these capabilities are there in this KSFD CUDA part of the MicroSim code, right? So MicroSim has this KSFD CUDA. So this is basically ours, and this has all this. So we have CUFFT MP, we have finite difference, and you can use multi-phase, multi-component, and now elastic stress effects. Okay, so for example, this is yesterday Abhik showed the comparison between GPU and his. Obviously, he had 960 CPUs. He had much more flops than we had available. But even in that, we could. So he told he boasted about this 8 hours, while we take like 16 hours. But that is fine because we cannot use so many GPUs currently. Currently, we can use maximum of 16 because of not our problem. It is because it is not available currently. Param Pravega also, I think you cannot use more than 16 GPUs at a time. So as you can see, the coarsening study on a 2000 by 2000 box, and you could see really, if you have seen previously, yesterday Abhi compared, and both came apparently the same. The only difference is because the initial configurations is slightly different. Other than that, the way the volume fraction evolved and all, these are all coming out to the same. So this is one of the capabilities, and that is solidification. Dendrite growth, and as you can see at one corner we have put a small seed and it's growing. And there also we have some benchmark on tip radius and velocity for all models, which come out to be very nice, and that has been discussed before.
We can't hear you.
Hello, are you able to hear me?
Yeah, now we can.
Yeah, so you have you can do the elasticity solver also in 3D for this multi-phase, multi-component elasticity, and we have some splitting movies. I don't know the splitting of gamma prime movies which use the same solver, and we have also done this 3D LZ and dendrite isothermal, right? This is isothermal condition. Yeah. So, and what 13K undercooling is it?
Sorry.
13K undercooling, is it?
Yeah, 13 Kelvin undercooling.
Yeah. So, but this took a lot of time. So I have my ParaView open. I hope that I can show some movies here. So this is, I think, 640 cube, but also Sauav has done one with 1024 cube. But the file size becomes a bit large. So you require some computing capability to post-process those files. You require like a good supercomputer with some good amount of GPUs to post-process those files. Right. So, but you can do it, and with HDF5 you can basically store the data. Those are all fine. Only thing, we require a ParaView server. In NSM also it is currently lacking. We do not have any server for visualization. Right. So we have to use our own cluster to do that, and that's current state of the art. Now you have. So as I told you, this is the multi-phase, multi-component KKS model, Kim Suzuki. So you have conserved composition field, and this I denotes the index of the element that you are using, index of the component that you are using. You can have multiple components and you can have multiple phases, right, which is denoted by phi. As you can see the symbol, the MicroSim symbol, the logo, that phi. So this is the phi that we are using here. So that's the non-conserved quantity, and you have this total free energy functional. All these things have been described in the other earlier talks, so I don't want to spend a lot of time on this. But yeah, as you have the bulk chemical part, the interfacial part, and the elastic, right? So this is the chemical energy, chemical contribution of individual phases. Then you have the interfacial part, that is basically to the grade again, here we are using KK's formulation. We are not using the exact Khan-Hillier type of formulation where we take exactly, you know, like this kappa, that is a physical kappa. We are using the interfacial energy, and we are using a much thicker interface width. However, if you do the asymptotics, you can easily understand that it basically recovers all the basic the sharp interface characteristics. Now you have also the elastic contribution that we have included in this list. So we have a set of equations that we solve. This is the Allen-Kahn equation. That is the for the non-conserved fields. And remember that the constraint that we put in is the sum of non-conserved fields at any point is going to be equal to unity. And then there is also this diffusion equation. Again, we have multiple components, and Mij is the diffusivity matrix. There's mobility matrix basically, which is related to the diffusivity that you measure. You can measure experimentally, and you can derive experimentally, and then basically you can incorporate the Mij. So yeah, Mij. So all of these you can do, and then you have also, because of mass conservation, this how this are distributed. We use an interpolation of HP. This HP you can take like a fifth order polynomial, or you can take like the phi square 3 minus 2 phi also. Means you can use double obstacle type of potentials. You can use if you use double, you can use different types of HP basically. So you can use like phi cube 10 minus. We are using this 15 phi plus 6 phi square. You can also use HP, which is like phi square 3 minus 2 phi. So you can use various such interpolation functions. Then obviously this is a diffusion potential basically. So this is something required, equality of diffusion potentials at the interface. So basically at each interface there should be the equality of diffusion potentials across for all elements across this given number of phases that you have. So, and you can have different types of interpolation functions, as I was telling you. So you have like very really complicated one, and you can also have this G-phi. There is one G-phi term, okay, which basically gives you. So you can use multi-well. What we are using here is multi-well, and you can also use multi-obstacle. In GP model, I think both are implemented. In KK's model, currently we have multi-well potentials. We still do not, but multi-obstacle is not a very big deal. So we are going to soon implement both multi-well and multi-obstacle. Currently it is multi-well, right?
Yeah.
So now comes the part which is elastic stress effects. Again, already Abhik has talked about. Remember, here only difference with Abhik's the way it was implemented in real space. So he implemented in real space with the iterative solver, which actually is quite easy. But in you can also solve it in Fourier space, and it becomes like a one-step solver when it is when you use a homogeneous modulus approximation. Obviously, if you do not use a homogeneous modulus approximation, then it can become iterative. Now, as you know, the elastic energy density is given by this, right? Sigma half sigma into epsilon, where epsilon is the elastic strain tensor, elastic strain, and elastic strain is again the difference between the total strain and this eigenstrain. The eigenstrain is the stress-free transformation strain. How does it come along? I will just show you a picture. You will be immediately understanding what happens. Why during precipitates, in particular in the solid state. In the solid state, when you have precipitates and matrix, coherent precipitates, and your lattice planes are directions are continuous. Why do you see? Because these precipitate phase and matrix phase have difference in elastic constants. You get these coherency strains, and we will show you how these coherency strains can be accounted for. This is how this can be accounted for. And so this coherency strain is basically the stress-free transformation strain, we also call it, or we call it eigenstrain, and it can be like very generalized, right? It is a function of phi we have used. Although Abhik has also explained that naturally it comes because of as a function of composition, but again, since we know the composition partitioning and we can track it, we can basically calculate it and we can put it. Hello, is there some sound? Some
noise came from someone.
Yeah, so I would ask others, means the other participants, to just switch off currently during my presentation. After that, you can just go ahead. And see, remember, we have also the capability to use a position dependent elastic stiffness tensor, and okay, and we can have a very generalized eigenstrain where you can introduce this tetragonalities, right? And this is the principal form of eigenstrain. And again, and then we solve the force balance equation, that is grad dot sigma equal to 0. We can also include grad dot sigma plus b, where b is the body force. And then there is this guy called Khachaturian, who wrote a really nice book on theory of structural transformations in solids. And basically, if you look at that, this is the HLB problem that is what he's solving, but he solves this problem, or the problem is solved using energy from the energy point of view, not from like the way we find displacements and then we find strains and then we find stresses. That is not, but we directly go to elastic energy and we try to minimize the elastic energy. This is how Khachaturian solves it. So as you can see here, the idea is very simple. You have a matrix and you have like these regions which are undergoing transformation. You punch it out. Okay, this is exactly Eshelby's formalism, but Eshelby's formalism is what he used to write the entire thing in the energy from the energy point of view. Now you take it out and you allow it to transform, right? And you allow it to transform. Now, once you have allowed it to transform, the holes are still circular, but your shapes have changed and all this stuff. Now you want to put it back, so you give some surface traction, right? You are giving, so you are giving some surface traction here. So it comes here. So you have this traction. Now you are allowing it to just release. So if it means relax, if it relaxes, then you get into some shapes here, right? And that is the entire. This is the basis for writing Khachaturian used this as the basis to derive his microelasticity theory. I'll tell you how it is done. It's actually quite easy. As you can see, if I write this, right? So L sigma ij L xj equal to 0. Now sigma ij is equals to Cij KL. Again, I am taking homogeneous modulus approximation here. So basically, precipitate and matrix, we are assuming it to be having the same modulus. It is actually a good assumption as long as we are looking at like Bickel-Bess superalloys and stuff. I don't know, in some cases, there may be, in some cases where you have really elastically stiffer phases and you have elastically softer phases, then definitely, you require to take into account the homogeneity in the modulus. So now Cij KL, KL plastic, and this is a part, means I'm in position. And remember, we are taking periodic boundary condition of x u of x plus L is a period, right? L is the period. So we are using periodic boundary conditions. Now this epsilon, I can basically, as I told you, there is a epsilon total, and then there is the E, which is like the macro strain, and then there is this eigenstrain, which is 0. And okay, I'll come to this. So basically, if you want, I will derive this and I'll show you. It's very easy. You just have to write this way, del sigma ij, right? So it is. So you will use 1 second. Remember, this is position independent. E is position independent. This is a function of R. This is also a function of R. And epsilon T in the sorry. See, I require a eraser. Okay, so I'll just one second. I'll just go to a new slide. So I'll just. It will be better if I can ink it. Are you still able to see?
Yeah, we can.
Yeah. So as you can see here, you can write epsilon. So remember, this is apparently Greeks. I don't know. Greeks might have two epsilon. So what this is called var epsilon, and this is the normal epsilon. So this is what I am using for this one is what I am using for eigenstrain. This one I am using for total strain, and for small strain approximation, I can write this. One sec. Epsilon t equals to half epsilon t. Say I write kl half tail uk tail xl plus tail ul tail x k. And also remember, because of symmetry, you can write the Cijkl is the same asCijlk, right? So Cij. Now, if that is so, I'll just insert one new slide. I don't want this thing. I don't want also this thing. Yeah. So now you see, if I write del sigma, column del sigma ij del xj equal to 0, which I can write as Cijkl. I can take now, and sigma ij again, as I told you, I just write Cijkl. And so I'm just writing this so that you do not forget what I am doing. Epsilon t kl plus ekl minus epsilon 0 kl means I'll just quickly show you, then I'll be done with it. And del sigma j del xj, if I do, so this becomes equals to del 2 Cijkl, and you have del ui del uk del xl, right? So del 2 uk del xj del xl, and remember the when you write with the derivative, this is position independent. This is the macroscopic strain, okay, which comes from homogenization. So this guy goes to 0, and the over, and remember another thing, another very important thing, that this total strain, this perturbative strain component goes to 0, and that defines the EKL. Okay, and you have this eigenstrain, which is again position dependent. So this equal to, this comes as Cijkl, and this will be epsilon kl 0. Okay, now what you do is you take Fourier transform of it, so you get Cijkl. I will use KJKL, but you can actually use, and you should actually use NJNL and mod K square and stuff. But yeah, CIJKL, KJKL, UK, so KJKL, so UK tilde, right? So see, remember one thing, that is Fourier. If you do derivative in terms of in Fourier space, then what happens is, say for example, I have a function f. Okay, and df dx is basically what I am trying to find. Now df dx is Fourier transform. If I take the Fourier transform of df dx, this is equal to this I here I equals to root minus 1, I, and then k is the reciprocal space vector. right? Ik f tilde. Okay, and if I take now d and f dxn, means nth derivative of the Fourier transform. If I take the Fourier transform, ik whole to the power n f tilde. So you see, in the as soon as you go to Fourier space, finding derivatives becomes very easy, right? And k, as you know, has a reciprocal relation with r, that is the real space. And now you can see here you have this del 2 uk del xj del xl, and this, if I take a Fourier transform, then basically I have this kjkl, right? That like k squared. So right, so because this is ik whole squared, right? So basically you have now two indices. So one index it goes to kj, another index go to kl, and you have uk tilde. So you have this term, and you can have uk tilde, and then you have like cijkl, again it's a constant, and you have epsilon. So I can write this as some sort of an very strange fictitious stress. 1 second. And write it as sigma 0 ij, right? It will be sigma 0 ij, no? But there is a del. This is missing. So you have del xj here. So del x, so cijkl del 0 del x. 1 second. Here I have to be careful. CIKL, x and KL is there, and here you have del 2. So here also you will have here it became del 2 because of this, but here it will be just del xj, right? So you will have now 1 second. You have to my God, 1 second. Let me just derive it. Sorry. So it is becomes cijkl. Now del xj, and this becomes epsilon kl, right? So this also I am taking Fourier space. So this part has become this cijkl. So and uk tilde, this is equals to cijkl. cijkl. If I take this together, I'll do that. I'll remove the CIJK and KL 0, and I'll just put here. Here I'll put sigma ij 0. Okay. Now it becomes very easy. So you have this term and you have this term, and this becomes CIJKL. There is no CIJKL here. This becomes, because I have absorbed this, right? I have written sigma ij 0 equals to cijkl epsilon kl, right? So now this becomes kj. Again, I am doing Fourier, and this is sigma ij 0 tilde, right? Correct? So sigma ij 0 tilde. Now you see, you have this term, you call it as gi. So this is CIJKL, KJKL. Now you see what is the dummy index, means which is repeated twice and which is a free index. So as you can see here, J and L are dummy indices, right? Because J is occurring here, J is occurring, L is occurring here, and J is here and L is here. Actually, a blackboard would have been really nice. This is really small space. I did not realize that. But anyway, so J and L are so you have GIK, right? So if you see CIJKL, yeah. So you can call it I see J and L are the, so this becomes GIK, and call it GIK inverse, okay? And it's a function of K and K, right? The K vectors like Kx, Ky, and Kz. So J inverse UK tilde equals to Kj and sigma ij is 0 tilde, right? So uk tilde just becomes equals to g ik, I'll take it here, g ik kj sigma ij, right? Am I correct? Yes, because see, this is one free index, it's one free index. That's it. Now you see, if you have this equation, you know the displacements. If you know the displacements, you know the strains, you know the stresses, and if you know strains and stresses, you know the energy. Now this is one part that I want to tell you. Again, if you want to know further, I will derive it step by step. Don't worry. This blackboard is very important. You know, sometimes this iPad thing screens. You know, I should have it would have been it should have been spaced out, and then it becomes very easy. So it's actually quite simple. It's not tough at all. So once you do that, hello. Once you do that, so basically this is what, for example, has been written. One here j is root minus 1, and this is your Green's function. So once you do that, and this is the zeroth order solution. If you have obviously homogeneous velocity, you have to go to higher order solutions and go into iterations and stuff. Also, you can use equivalent eigenstrain formulation. So there are multiple ways to solve this problem, this elastic stress problem. One of the easiest ways, so this is something that I did in my thesis. Okay, so basically it's like a 12-step thing. So I start with this, then I break it down. So I break it down like 1, 2, 3, 4, 5, 6 integrals, and I know the displacement solution in the Fourier space. So in each of these I use Percival oscillations, and then after 12 steps I go into this, right? So you have this interaction term bpq, and these are basically your that h phi or phi in Fourier space. Remember, this theta p is nothing but like h of phi, okay, and theta p tilde is nothing but this h of phi tilde. So that's the idea. So these are basically eigenstrain. If I tell you eigenstrain, the function of r, which I am writing as some constant part of the eigenstrain. Let's call it this one, and then we have phi of, it can be phi of r or a function of phi of r. It can be like a h of phi of r. Okay, so that's how we write it. So this theta is nothing but that. Oh my god, there is power off in our place. I don't know whether, are you able to hear me still?
Yeah, we can hear you.
Oh, good. So yeah. So if you have F elastic like this, if you see now, you have theta p tilde and theta q star tilde. And if you can see that I have excluded this k equal to 0 from the integration. And now if you do that, then yeah. So one means from Abhi only I got this idea that this is a very beautiful derivation that Abhi did. And then I found out that that is exactly what I used here. And if you see that you have F elastic, you just do this variation. If you look at Chaturyan, sometimes you may get confused. This way you don't get confused ever. So it becomes so easy. And you have this del F elastic del theta, and you just get this point. Okay. It should have been BPQ theta P. I think I missed. Yeah, because this is BIQ and this is BPI, right? So you get a BPI. Okay, here I have written theta I. Yeah, I am correct. I'm correct. Yeah, this is correct. So BPI theta P, and where BPI is, as you can see here, this is the term. Now, if you see here, this is constant. This part is the constant part of the eigenstrain. This part again constant part of the eigenstrain. This is your Green's function. Okay, and this which just function depends on n is like k by mod k, n here is nothing but k by mod k. Okay, so now you see this entire term, you can take it out of time loop. You don't require anything in a time loop. The only term that you have to look at is the the phi, right? Phi varies with time, but this entire thing can be evaluated outside time loop. And another thing, if you go to cubic elastic constants, like you have 3 independent elastic constants, these terms become very simple polynomials. So this becomes a very elegant way to solve the solve equations, particularly when you have homogeneous modulus approximation. Now, so once you have the elastic driving force, you add it to the KKS model, and then you just solve it. That's the idea, right? So this is the process flow. So as you can see, if you look at that, this is something that we have implemented in our CUFFT MP based solver, right? Saurabh, our CUFFT MP solver basically is using the homogeneous modulus approximation.
Yes.
But again, we have also a inhomogeneous solver, which will release in the future, which is again based on spectrum. Now, if you look at this, there is a process. This is the process flow. So there is a, as you have already seen, there is an in-file generator and integrator. Apparently, everything has become dark here. So, so, so you have the material. So you have the simulation parameters, boundary conditions. I'll show you demonstration, and then there is a filling function, and then you compile the code. Once you can compile the code, you can execute on CPU/GPU. So you can, in our case, we will execute it on multiple GPUs, right? So and you can turn on and turn off irrespective. And I think in the GP part, already they have the brain growth part implemented. So there is a flag to turn on and turn off brain growth, and then there is a visualization and post-processing too. Now, see, this is a, so here Saurabh can take over. Saurabh, if you want to take over, you can.
Yeah, I'll just explain this. So how we're implementing multi-GPU is that, like Sir said earlier, we're using CUDA or MPI. Right. Am I audible? Yeah. So we're using CUDA or MPI to link GPUs between each other to facilitate communication between GPUs. So CUFFT MP is actually a closed source software. CUFFT is an open source software. So CUFFT MP has a certain decomposition scheme which we have to follow. So what we've done is, since we have a finite difference implementation and for the equation, for the phase field equations, and just for the elastic part, we are using CUFFT MP. We have followed CUFFT MP's decomposition scheme, which is a 1D domain decomposition, as you can see in the diagram there. So what we are doing is we're decomposing the entire domain. Now let's say we have a 500 cube domain and we have 4 GPUs. We give each GPU 500 into 500 into 125, and so this is a 1D decomposition. We're slicing only along one dimension, and now we give each worker its part, each GPU its part, which is that subblock, and only the buffer layers, only the layers of, for a finite difference stencil, we need the neighboring cells, right? So when we're dividing over 4 GPUs, we have these neighboring cells which need to be updated every iteration because you have a new value which is being calculated. So we have a layer, a buffer layer. The blue one, the blue layer is the outermost layer of the block. So if you have a 500 into 500 into 125 block, so Z equal to 125 and Z equal to 250, all those are the buffer, not the buffer, they are the outermost layers. They've called it a cutting plane here. And then you have one more plane, which is called the buffer layer, which we copy the neighboring blocks cutting plane into. So this communication between the cutting plane and the buffer layer, we are using MPI. And CUDA over MPI, as you can see in the next slide, if you go to the next slide, is something which can bypass all these data transfers. So if you want to transfer from the GPU to another from one GPU to another, before CUDA over MPI, you'd have to first stage it in the host and then move it from one process to the other, from one CPU to the other, actually, since each CPU is what controls the process. And then you'd have to do another CUDA transfer. So this has a heavy penalty associated with it because the GPU to CPU bus, that's a PCI bus usually, it's bandwidth limiting. So what CUDA over MPI does is that it prevents all, it still uses the same bus, but it bypasses all the copies in between. You don't have to copy to CPU, CPU to CPU. So you just go directly from GPU to GPU via the same bus, but it saves a lot of time. So if you could go to the next slide. So this is just a scaling performance diagram we've created. Like sir said earlier, we have run up to 16 GPUs using Param Seva. This is a 500 cube system. It's a solidification problem, 4 Kelvin undercooling. So as you can see, the scaling is quite good up till around 10 GPUs, after which the slope of the speed up the speed, it slightly decreases. But this is on par with what you'll see in the literature. After 1620 GPUs, you have the communication overhead takes over. So you're limited by communication rather than computation at some point. And one important thing to note here is that so we've taken a 500 cube system. So if you take a larger system, the scaling may actually, you may see better scaling usually, because again, you also have a slight computation overhead which comes in. There's a slight interplay between computation and communication at certain system sizes. At small system sizes, you'll see it very quickly because each GPU will have very little work to do. GPUs have a lot of threads. They have a lot of cores. For example, the V100 GPU which we use, it has around 5,000 cores. So when you have a small problem, you have to use one GPU. If you use multiple GPUs, again, it will be slower than one GPU. So what I want to say is that
as Sauav is telling, continue.
GPUs are excellent at solving bigger problems. You want to give it bigger problems. You don't want to solve small problems with a GPU. You'll actually see poor efficiency at that if you try to use a lot of GPUs with small problems.
Okay. I'll go next slide. Yeah.
Yeah. So brief. This is just to save some time. I think we can skip over this because all this is I've just put it in the README.
Yeah. So I will come to the demo then. Then we will start with the demo. Only thing, please understand, we are using only V100. Apparently in NSM soon this A100 will also be implemented by the next year. And then A100 definitely there will be a more speed up. Only thing is not all the nodes in NSM have GPUs. We are requesting because most of these they have GPU capability, but they do not have the GPU card. So once you have those GPU cards, definitely you will see much larger problems than these. Even these are like these are something that we could not solve earlier. It was very, very difficult. Obviously, yeah, it can be solved with multiple CPUs. But again, remember, multiple CPUs or cores have to be available. Currently in Promega and all this is available. But yeah, so initially we had our own clusters, we could not. So we have gone to GPUs with the point of view of portability. But with a smaller cluster, can we basically, or with a small machine, can we basically go to very large perform very large simulations? So this is where this NVIDIA DGX machines and all these things are coming. We are acquiring some of these in near future ourselves. So we hope that we will boost the competition more. So without much ado, let us go back to the demo. So we'll start the demo. Remember, when you want to install, it's very easy actually. You please understand we are backward compatible, so we can go from 22.5 to 23.1. We have no guarantee whether the code will work when it goes to you go to higher version. Okay, if you go to higher version, I don't know means that becomes like we haven't tested it, but we will definitely test it in near future and tell you. So we up to 23.1. 23.1 is I think 2022 release, right? Sure.
No, January 2023.
January.
6 months. It released 6 months back. January 2020.
So this is the last release that we have tested, and we have tested on all of these, and we have this requirement and this requirement. This was anyway there. I think there is a singularity image we can tell for the GPU solvers also, right? The CUDA GPU solvers. So if you have that, then in your laptop, if you have a CUDA capable card, you can actually install it. Remember, you don't have even CU50MP can be run with one GPU. So there is no problem at all. You can just take down the singularity image and you can use the singularity image to run the things. Okay, so we will now start with the demos. Okay, so I'll switch from here. Just give me 1 or 2 minutes time. I'll have to go to the other part, other machine, because this is an iPad on which I was doing. So I'll go to this. I hope that everything will work fine. My screen. Hello, are you able to see my screen?
No, we can't.
One sec. But it is telling stop sharing.
You are sharing the screen.
Yeah, I am sharing screen from another computer. So I will stop sharing here. Yeah, I have stopped sharing there. So are you able to see?
Yes, that's the screen.
If you want, I can actually switch off on the iPad.
Oh.
Shall I again?
It's awkward. My face was there on four screens. I thought you were sharing the screen.
Let me just share the screen again. Are you getting now?
Yeah, we can see it.
You can see the screen, right?
Yeah, we can.
You can see the dendrite and all?
Yeah, we can see it. Yeah.
Oh, good. Thank God. I was thinking otherwise what will I do? Okay, so good. So we will first go into, so as you have already been demonstrated, so I'll open terminal. So we have actually some screen capture movies also that we made, because if anything like this happens, we will just play those movies. But anyway, we will try to do it ourselves. So it is in desktop, and I go to MicroSim folder, and I want to create this code. So remember, everywhere we have this MS, so it is already documented, MSENV. This is we can give any other name. So this is something, and then you have to just write Python 3 let's see, py create co open co tool. So I have set my resolution at 190/10, but you can go to higher resolutions. Means I can also go to very high resolutions here, but I have just given it so that you can see. Are you able to see clearly?
Yeah, we can see. It's clear.
Okay. So we are using this KKS GPU CUDA model. Okay, and I'll choose an in file, and then if you want, I can also create an in file. But I'll just here also we will make changes. Don't worry. So go to not in videos. We'll go to the input files, and maybe we'll start with the certification one. So we will use any one of these. So let me use this one. Okay, so you have now many of these things populated, but we will try to see as we go. So you have this simulation geometry, and the dimensions are 200 by 200, and right, we have a 200 grid points on x, along x and along y, and then you have a discretization. We are using like 1 minus 8 meters as the grid spacing along x and along y. Along z it does not matter because it's a 2D problem. And we have this delta t, which is 8 to the minus 9, right? And then I click on next. Then I have number of phases is 2 here, and you have like the solid phase is alpha, the liquid phase is called liquid. So I've saved it, and you have also 2 components here. You can go to more. We are using 2 here, aluminum zinc. So L and Zn. Save. Go to these are the numerical things like iterations, smoothing, time steps, and writing interval. So we basically we have the nucleus and we smooth it, and for smoothing we are using like 10 steps, and we are running it for 20,000 time steps. We can run it for say 30,000 time steps. Say we run it for 30,000 steps. Restart is 0. We are not restarting, and we are saving at 2,000 time steps, and we have a number of workers because I am using a single GPU here. One, Then I have the diffusivity. Remember here elasticity, although it is given, elasticity is not important. It's a solidification problem, right? Elastic, the eigenstrain and elastic constants, these are not important. You are looking at diffusivity. So if I look at liquid, diffusivity is 1e minus 9. But as you know, in solidification, what we assume is zero diffusivity in this solid because it's very low. So for alpha, we have used and we are using a diagonal matrix, and we are giving zero diffusivity. For liquid, we have given 1 minus 9. Then we have the gamma 1, 2, the interface energy is 100 millijoules per meter square. Then R is 8.314, guide because of gas constant, at this 1e minus 5 or 10e minus 6 is the molar volume. And then we have we are using function F3, which is like a parabolic approximation, but it is all the data is coming from this alznme.tdb. So this is the TDB file, and we remember TDB phases, whatever is written in the TDB file, it's already explained by Avik and Fanny and all. So I don't want to go into that, but you see, you have FCC A1 and liquid, and phase map is also that, and you have two phases. Right? These are two thermodynamic phases. You can have more phases, like if you have you can have multiple grains, for example, but the thermodynamic phases are you have the space composition, that is basically, as you know, these are your coming from the phase diagram. So you have 0, 0 is 9.926, and that the interface 0.817, 0.817, and 1, 1, that is 0.817. So basically, and you have an angular rotation of the seed 0, 0, 45 is the rotation, and then go to the boundary conditions. We are using Neumann boundary conditions, zero flux boundary conditions for phi. We basically in K case we solve for phi. When we solve for C, we are not solving for mu, but they are also there. We are also not solving for T, although you may solve also the temperature field. I haven't solved it here. So this is isothermal solidification with 13K undercooling, right?
Yes, 13K.
So then we go to the domain filling. So we have already a filled shape. We will just show you that. If you want, we can change it also slightly. Go up. MicroSim Workshop. It is in the input files. This one. And this is the one that we are using. Okay. So you see, we have a small particle, spherical particle at at 0, 0 at the origin, and with the radius is it has 8 grid points. So if you see edit, you'll see immediately you can start with 8 grid points, you can start with 10 grid points, whichever you want. So center, the point is basically 0, 0. So this is what we have used, and then but if you want, you can also change. And then we are using the KK's GPU CUDA model. So this is the model, and if you click on this, you will have model specific parameters. We have only one page of model specific parameters. So this is the equilibrium or filling temperature. This is the undercooling. See, you have 13K undercooling here. You can clearly see that. And here gamma ABC is 0 because although we are using a multi-well potential, we have only two phases, so there is no need for gamma ABC. The elasticity flag is taken to be 0, grain growth flag is taken to be 0, and we have used a track progress at 50, and we are using, currently we are using right format as ASCII, but you can use binary, right? So you have both options, binary and ASCII. So we are using ASCII, and we have 4-fold anisotropy, and the strength of anisotropy is 0.0. Now you have this. I'll create, say now new name. I can create, say for example, input 2.in and fill in 2.in, because I have changed at least the number of times that we will run. So that is we will. I hope that it will finish very fast. So now we have generated the file. Choose in the folder. These are all saved. Now you have this thing called run. Click on run. I hope that everything was fine. it's just compiling. So create the executable. It will create the executable, and once you have the executable, remember we will run with number of processes 1, because number of GPUs here we are using is 1. If you can also use 2, by the way. However, what will happen is the code will run a bit slow because you have 1 GPU. It will divide the 1 GPU into 2 GPUs. Obviously, it will become slow, right? If you have physically 2 GPUs, use 2 GPUs. If you have physically 4 GPUs, use 4. So that's the idea. So it is quite fast, I think, because the system size is too small. So as you can see, the alpha and liquid, the max is, see, you can get like 10 to the minus 16 minimum. That is like 0, and max is like 1. So everything is perfect. Means things are working quite nicely. Done. So it's actually quite fast. You see, even portable, although it's a small code, the GPU, the codes do run fast. So anyway, so I'll just open now the MicroSim tool, and then I'll click on. So yeah, Sauav, you have to also help me. So this is the
import ticket.
And that's what I'll do. And then I have to go there. Go to the input files. This one, data. This one, right? Just have to use that. Okay, that has all imported everything. I'll start. I could have run a little bit more, but it's okay. Yeah, you can do this, and then you can also see the font velocity and stuff. So, for example, this is the average font velocity. So all these things you can do. So there are, as you know, there already this has been discussed. There is this post processing tool is quite beautiful and comprehensive. You have lot of functions here. You have the tip radius, velocity, all this stuff. So we will go to the next one because we want to show several. So let us go to the next part. So I'll close this.
You can press the MicroSim logo.
Okay.
You can go back.
Yeah. And then I'll import a new file. Now this is for again the same model. New file. See, in general, what we do is we often use command line. We are not, but there is this beautiful GUI which can be used by users. But yeah, many times we just run it with like make run and stuff. So, or we generate. See, there is a script generator. You can see. You can use that script generator and you can put it in your Padam Pravega or Padam Seva or whatever. Now again here I will use this input in ILMO single dotting. This is like one precipitate. We are putting it at the center of the box. We are allowing last setting, and we want to see whether due to elastic stress effects, whether there is a shape change or something as the particle.
You can pick input B. That's a slightly bigger system.
Yeah, input B. Yeah. Okay. Yes. Yesterday we were doing input B. Yeah, it's a 300 by 300 system. 200 by 200 is too small for a GPU. So your delta x, which is 40 minus 11. Remember here, see, immediately you can see we have elastic stress effects, we have coherent interfaces, but we have also used the delta x and delta y. These are slightly more refined than what you have used in solidification. Okay, so that's the idea. So you have the delta t of 2e minus 9 here, and then I go next. I have two phases. So what are the phases? Alpha and beta. So and you have three components: an AL, MO, and NI. NI is the dependent variable. Okay, so this is like a superalloy. So it's nickel-based superalloy. So you have AL and MO as the two other components. So now the next step, we have gone to 50,000 steps now. 10 is the end speed, and so yeah, we initially had like 10,000. We thought, I told 10,000 is too small for it's like an insult to a GPU. So restart is 0 and you have no more tests. I'll use 1 and then I go next. So again, as you can see here, so what we are doing is we have this is the phase diagram, and as you can see, there are two compositions. One is the aluminum concentration. This is the molybdenum concentration, and this is again aluminum molybdenum, and this is the 0, 1, that is the interfacial equilibrium compositions. Again, this is 1, 0, and this is 1, 1. These are the compositions of the, I think, the beta phase, right?
Yes, beta
phase. So and you have no rotation matrix here. So you have the gamma, which is again we have taken here. Remember, there we took 100 millijoules per meter square. Here we are in the precipitation case. As you know, coherent interfaces have very, see, this is something that you have to take care. You have to take care of the physical. Means if you are looking at a physical simulation, you have to also look at this physical properties. Like in coherent interfaces, it can be like as low as 10 millijoules per meter square. So we have used something like 10 millijoules per meter square. And then you have the function f, we have used 4. So remember, we are using a so what do I call it? I'll call it like an encrypted database. Let's call it encrypt. Basically, the data is already read from, say, thermocalc or pandat. So we have this data, we have spline fitted the data, and data is like basically like the composition as a function of temperature. So we have the phase diagram data there, and we have also the corresponding energies, and we have two phases. One is this is the gamma prime phase, which is called so there are two phases here. If you see very carefully, one is FCCA1 and the another is FCCL1, right? So that's the thing. So you have, so the way it is written is like very, so yeah, this is again based on exactly the whatever is written in the thermodynamic database. However, this is an encrypted data. It has already been generated. It has kept in a CSV file, and we are using it. Right? That's why we are using function f4. This again, these have been explained to you, so I am not going to explain again.
You have to go to diffusivity and elasticity now.
Yeah, I'll do it.
Back. You have to go back.
Oh,
material parameters on the left.
Oh, that I did not do. Huh?
The first tab.
Oh, this I did not show. Okay, third. So, diffusivity we are taking to be the same for alpha as well as for beta. See here, basically we are looking at precipitate in a matrix. So diffusivity for alpha and beta, there is no difference. We are assuming no difference. So for alpha phase as well as for beta phase. So as a result, the solute trapping type of problems are not really that much in the precipitate space. And see, we have taken an eigenstrain of, say, it's a dilatational eigenstrain. This is called dilatation. That means like the beta phase is the matrix phase, alpha phase is the precipitate phase. Alpha phase has a dilatational misfit, and that means it has like bigger lattice parameter along x and y by 1%, right? Bigger than the, so basically it's like a cube. You are dilating it. You are not basically, if you want to make cube to tetragonal, that is also another example that we will show. But here it is like cube to cube. That is the thing. So it remains cube, but it's a bigger, it's like a slightly bigger cube. The alpha phase, the precipitate phase is a slightly bigger cube than the beta phase. Again, it can be a smaller cube. So then the eigenstrain will become negative. So for example, here, we can actually try that. Why not take a risk? So yeah. So
the beta phase has to be 0. The matrix we set eigenstrain 0.
Matrix phase are eigenstrain 0. So this will put minus 0.01. 1 second. We will put negative eigenstrain. So that means the alpha phase has smaller lattice parameter. Okay, and then you have all the other components 0. This is dilatational, and then for beta, I'll take all are 0. Okay, and this is again, this is the elastic constants we have already filled, C11, C12, and C44. If you see the Zener anisotropy parameter here, which is 2C4, 4 by C11 minus C12, it will be roughly like what, 3.3 or something?
Exactly. Exactly.
Oh, exactly 3. Okay. So yeah. By the way, for gamma gamma prime in general in this type of system, it can be like 3.3. But yeah, it is 3 here. We have exactly taken as 3. And the eigenstrain is taken to be, so for the matrix phase it's 0. And again, just checking, alpha phase is this, right? Now we have gone there. We have gone finished the material parameters. Boundary conditions, we are taking, as I told you, we are using periodic boundary conditions for P. And here we are solving for P and C. Both cases we are taking periodic boundary. Next. Yeah, we already have a shape with us.
Filling B.
Huh?
It'll be filling B in that folder.
I know. So this is the elastic single, right? So
Yes.
in filling B. Yeah. So we have filling B. So the 10 is the radius, right? 10 is the radius. And 150 is the center, is it?
Yes.
Oh, yeah, it is 300. Yeah, okay. Sure. Yes, that's right. So we have done that. Now go next. We have the GPU model. The PK is GPU CUDA. When we go here, we are writing in ASCII. Track progress is a 50. We have no anisotropy interface energy currently here. And this epsilon is basically the interfacial width that we are taking. And we have an equilibrium temperature of 1200, and we are taking a undercooling of 100 degrees, which will give the supersaturation. And as a result of supersaturation, the precipitate will grow. And as it grows, it may change its shape because of elastic stress effects. And the elasticity flag is taken to be 1. I'll go to next, and then I'll generate the files.
Right. You can choose this.
I can choose here only, right?
Yeah.
It will be over. Filling 2.in. Then you can start. So it has 50,000 steps. So again, it will compile. Compiling it will take same time. Running it will take slightly more time, but not that much. So it is running now, and as you can see, things are doing pretty well. And, so what you will generally see, whether it is negative eigenstrain or positive eigenstrain, look at this. Elastic energy is C times epsilon squared. So as a result, the energy magnitude of energy does not really change if you change the sign of misfit, but there will be some changes. Say, for example, if you apply stress, there will be some changes. So negative misfit we will show you later means that it has some particularly when we apply stress and we want to run simulations, say, and we get into drafting and stuff. So there, in that case, the sign of misfit matters a lot. And here again, it's a two-phase system. So here, let us see whether it will matter. It is taking a little bit more time than I anticipated. But nowadays, many laptops, this is one thing that I can tell you, that many desktops and laptops come with very good GPUs. These RTX GPUs are quite cheap also now. So you can particularly companies can easily buy such desktops. And then there is this DGX station, that is NVIDIA, which has this CUDA capabilities. Again, another thing is possible. For example, we are using Param machines from NSM. I think it is also possible for you to buy computing time on these clusters and run our codes and test them. So I feel that definitely it can be used for many of the challenges that you face in your industry, and I feel that it would really also definitely it will help academia, the students who are here. But not only that, means it will also be of very useful for industries. It is taking slightly more time, sure, right?
Yeah, because we're running for a longer time, it's a bigger system, but it's still quite fast for a 300 square, 50,000 times if you're running.
It's done. Yeah. No, I was thinking then the honest code is not coming. So anyway, so we go to now the MicroSim tool, and then I go to this one. You have to remember where it was. It was in this one, Elastic Singular. Data. It has been
0.
Output 2,
yeah.
right?
Output 2, yes.
Yeah, done. So as you can see, it is trying to become cuboidal as it grows in size. So I don't know why this guy is there. So if you increase the eigenstrain a little bit, then you will see that it becomes much sharper. The edges become much sharper. But here you can definitely see that it has. And remember, the AZ is 3. That means the 1, 0, 0 directions are the softer directions. So you basically see the alignment that way, and you basically see this cuboidal type of a particle. Okay, so I'll go back, but there was this other thing that we could do.
Precipitate size.
Precipitate size.
So plot all. You can do plot.
Yeah. So you can see the area, how it goes, the radius, the aspect ratio remains how it is. So and you see all these different parameters here. So you can plot all of them. So that, and you can also download as a CSV for further processing. So these are the stuff that you can do. Now we'll go into an example of precipitate coursing. So again, I'll go back to this tool. Back. But I remember that we increase the misfit strain in some example, no?
Yeah, we can. This one we've taken 0.01. If you want a sharper.
Yeah. So no, but if no, that's fine. Not required. So we will go to the next one.
We can show the 3 variant case that will have coarsening, multi-particle coarsening, and
yeah. So this is here. That's what I did. So here we took the filling new dot in. Yes. Filling new dot in.
Input new dot in.
Sorry, input. So yeah. So this is a 400 by 400 XY, and this is dimension 2. And you have these are the space and time discretization values. Number of phases are 4, as you can see, gamma 1, gamma 2, gamma 3, and gamma. So gamma is your
the matrix phase, and
matrix
gamma
phase,
1,
and gamma 1, gamma 2, gamma 3 are the 3 phases, 3 variants basically. But yeah, these are the 3 phases, and they vary in the elastic the eigenstrain. We will come to that. So that's the thing, and you have also 3 components here. So you can see you have here we are just putting ALMO in, but it is more like titanium, aluminum, niobium things. But anyway, yeah, we just put some names. We can put anything. So you have 20,000 time steps here. It will take a little bit of time. You have to be a bit more patient. And save at, we are saving at the 1,000 time steps. And we have the material parameters where this becomes very, very important. So as you can see here, the diffusivities I don't change. So I'm not looking at the diffusivities here, but we have to be very careful with the eigenstrengths. So I have to now choose the eigenstrengths correctly. So I will choose 0.02 and minus 0.02 for the first one. Okay.
Yeah.
And then we are doing the 120 degree and 240 degree rotated. So let us go to gamma 2. Now you have to calculate and tell me. I can't do both.
Yeah, I'll give you a second.
So it will be minus, I think it will be, first one will be minus 0.01. Right?
Yes, minus 0.01 and plus 0.01. The 1, 1 and 2, 2.
And the last one, that is the 1, 2 will be?
Yeah, that will be plus 0.0172. 0.0172.
1732. Hey, see, this is the problem. All this UI cannot solve my I problem. So as a result, I don't know sometimes what I'm typing. Yeah, now it's all fine. So
yeah, there's a space between the decimal point and the 0. You can remove that space.
where,
The last
where?
one. In the 1, 2 eigenstrength.
Oh, what happened? Oops. I'm sorry. 0 point.
There's a space between the decimal point and the 0. Oh, sorry, there are 2 decimal points. So you can go back a little bit. You can backspace a little.
No, are you seeing now?
Yeah.
I don't know why this. Because I type like blind, but yeah. So this is correct, right? This is plus, right?
Yeah, plus.
Minus 101 plus 101 and 0.01732. Yeah. So this is gamma 2, gamma 1, gamma 2 is done. Now gamma 3 we will do.
Same as
So
previous. And then you can change the sign.
one second. Gamma 2 is minus, and yeah, gamma 3 also will be minus. Minus 0.01 plus 0.01, and this will be minus
0.017.
0.01732. So, and this is my elastic constants, minus 0.01732. Okay, and for gamma, that is the matrix, it will be 0. Matrix has no eigenstrength. Means we are assuming that, right? We are taking matrix as the reference phase. As a result, we are putting. In fact, you can also put, say, average alloy composition as the reference. It's up to your convention that you use. So you have this diagonal. So the diffusivities we don't care about. So we go now to the gamma. We are using the same interface energy between all the variants with the matrix space, as well as between variants and between the two variants. But yeah, between the variants, it should have been okay. We will look at it later. But yeah, so you have function F4 again. You have 2 phases. Harmonic 2 phases are there because they are. If you remember, I told you that these are basically 3. So these are basically 3 variants. We should have actually used isotropic elastic constants, but yeah, this is fine. This is one example that we are giving, and we have this phase composition properties for NI. These are like the two independent components, and there is the dependent component, and again these are the rotation matrices, and then on the boundary conditions we are using PVC for phi as well as for C. Then we have domain filling. Here I will import it. Okay, in this case I will import it. So basically import the shape, which is basically given in this MicroSim Workshop. MicroSim Workshop videos, 3 variant, and
Filling new.
So we have created C for 0, 0, 0. This is corresponding to gamma 1, 1, 1, 1 corresponds to gamma 2, 2, 2, 2 corresponds to gamma 3. You can also use random. We are not doing random here. We are just giving three variants of each, and we are running it. And so you can see that. And then we go to next, and then we go to this one. Here we have ASCII, and all these things are similar as previous. Again, we have 100 K out under pulling, and this is the width, and elastic is turned on. Next, then we have this. So we call it input new dot in. Say no, you input 3 dot in. Filling is the same, right?
Yeah, filling is the same.
No, filling new dot in, no.
It will generate. It will generate any name.
Filling 3 dot in and output 3 dot out. I'm just generating all these things. Okay, and then I'm generating the files. Where do I generate? Here. Okay. Now I'm done. So yeah, so compilation time remains the same. Exactly the same code is compiled. So you can see the solver has everything. It has multi-phase, multi-components. You can switch on and off elasticity. You have like one complete solver for all your phase field problems. Microstructure evolution. And you see there are so many 5. I think we are now with Ambrex and OpenFOAM and all. We have a large number of solvers. I don't think that anyone has this many variety of solvers in the world. I don't know. Abhi can comment on that, but I think there is none. So much variety.
There is none.
Yeah, there is none.
We already have the file saved. We can directly go to the MicroSim tool.
Exactly the same file saved. Do you remember?
Yeah, exactly the same file. Yes.
How do I go to the MicroSim tool now?
Now you can go to model parameters.
It was running, everything was going fine. See, I am not as.
No, Saswata, just go back. Go to post processing.
Yeah.
Close this.
I want to close this because yeah. Can I close this?
Yes.
Yeah, you can. You can press the big X.
This one, na?
Yeah. And now we have to import that in file. So the first.
So that's what. See, exactly. That's what. But yeah, it's very convenient.
Input 3. We have to get the in file first.
Input 3. Now I have to go there. I don't know why it is not. Yesterday it was going exactly again to that file. I don't know why suddenly it is not. Data 0. Input 3 means output 3, right?
Yeah, output 0. You can click on output 0.
Output 3 is out. No, this one.
Yeah, the one above that.
You are sure?
Yes.
Okay. Okay, so this is gamma 1, this is gamma 2, this is gamma 3, this is gamma, which contains everything. The matrix space, as you can see. 1, 2, So you can see the different orientations. Elastic constants, we should play with it. It goes more like spheres if you can increase a little bit of the elastic constant. You have to also run it for slightly longer time. And you require to pack more, but we could not because of the time thing. So anything else we want to show? Shourav, you please tell me.
So now we've covered multi-component, we've covered multi-phase, we've covered solidification and precipitation. So you can show how to load 3D files in ParaView. And
Yes.
I also wanted to show how to convert a 2D file to 3D file, since currently that's not possible through the GUI.
Now
so I can demonstrate that on my system.
You want to open on your system? You want to share? I will stop.
You can just open any input file. I'll just demonstrate. Any input file. The solidification one.
Okay. Okay. Solidification one. Now
Yeah, input file is, yeah, so you can go to videos. You can go to solidification.
Videos. Okay. Videos. Then I'll go to which one? Solve ALZN.
Yes.
Okay.
You can open the input file, the .in file.
Which one? You tell me that. This one? Yeah.
Yep.
Then open with text editor?
Yes. It's quite simple to convert this. For now, you'll have to, if you want to run 3D simulations, you'll have to run via the terminal. Instructions for that are there in the README. So there's only a few modifications you'll have to make. So first you'll have to change the dimension to 3.
I'll change it 1 second. Yeah.
Then you can change mesh Z to 200. And you can give a delta Z which is equal to delta X. That's 1E minus 8. So you can reduce the delta T a little bit. What we are seeing in our simulations is that sometimes 3D simulations require a slightly lower time step. 2/3. You have to use 2/3 of the 2D simulation. So 14E minus 9 works.
12.
Yeah,
2/3
12
means
or
12 now.
Yes.
2/3 means 2/3 of 18 is 12, right? Yeah.
Yeah, I've tested till 14, which is why I said 14.
Okay, 14.
Okay, so now you can go down to the boundary conditions. That's line 35. So you see the 2 zeros, those are free boundary conditions, which basically tell the system that it's a 2D system, that nest Z is 1. So we'll change that to 1. We'll give Neumann boundary conditions for everything. So we'll make the 0 zeros 1 1 for all the 4.
Yeah, but for us it is only phi and C, no?
Yeah, so we'll for the KK solver we'll only be reading phi and C. But in the future, when if we'll support
for the GP solver, yeah, we want to go there. Yeah, exactly.
And can you go down? So all this does not require any change. You can keep going down, and that's it. So you have to change the boundary conditions. You have to change the delta X, delta Z. You have to change the mesh Z, and you have to change the dimension. And
now,
then
do
you
I
can
run it now?
It's a little large. It'll be difficult to run.
Yeah,
but we already have
yeah.
So we can show them the VTK.
Yeah, we will show you the VTK. Yeah. So the point is, I have now all the things. So shall I press and run?
That it's a 640 cube simulation.
So remember, if my machine hangs, please don't blame me. I'm just playing it. Let us see. Oh, it is again going back. I should have gone to the next frame. My machine will hang. See, you please tell that for these viewing, this is a laptop on which we are doing. You cannot use a laptop, even though the laptop is quite good. You require a good desktop for visualizing 3D and all. This is very important. Or you should have a ParaView server. Because 3D is intensive. See, it's now gone. everything was there.
No, so what happens is these are 640 cube isosurfaces that you're trying to generate. So there's a lot of points it has to cover.
No, it has already generated. No, it generated over half an hour.
Unfortunately, ParaView regenerates it every time you go to the timestamp.
Yeah, it's a very so
Doesn't
that
crash.
way that way the tool that is developed is awesome. It has to be extended to 3D. I feel that will be like a really awesome thing because ParaView has this problem. It again replots everything, reloads everything, and again creates isosurface. I don't know why. Or we should use a ParaView script and keep it with us. Do you have it, Saurav? Then we can just show. I think it was there in our cluster.
Yeah, it's there, but even that will take a little bit of time. I think we can't show it in the time that we have. So,
Okay. So then we can ask people to ask questions.
If there are any questions, I think we've covered everything we wanted to cover.
Yeah, means most of the things that we wanted to cover. There are obviously I wanted to show like a full-fledged coarsening simulation in a 1000 by 1000. That is also possible, by the way. We will give all these examples. Please understand. Hello.
Yeah, we're able to hear you.
Yeah. So is anybody else? If people are asking questions from that side, can you please help me?
Yeah, there are no questions from here.
Physical questions here?
We can. I don't think there are any questions from the virtual participants either. Yeah, we can wrap up in that case. I think there are no questions.
No, I don't know. In chat, is there any question?
No, there are none.
Okay. I think people are already very tired.
No, thanks, Saswata. Nice.
Yeah. Okay. Yeah. Now it's coming. Wait.
Yes, it's almost low. To load all the geometry faces and everything. There's just one thing that loaded.
It's going to load 0 now, which is a small, tiny precipitate in the corner.
Absolutely. If you have just gone to the last frame and the.
No, this is the last frame.
This is the last frame.
Some middle frame by choosing the time.
But how do I go back now?
You can't.
Now it has started. It will start. Just give 1 more minute. Yeah, it has gone back to 0, 0. Are you seeing, Saurav?
No, it's frozen here.
Yeah, no, the contour hasn't disappeared yet.
Contour will disappear. Just give 1 minute. This is a laptop. Please understand.
One of the challenges with 3D simulations. Anywhere you do, there's a challenge.
No, because this is a no. This is not a real challenge actually. This is an apparent challenge because I am using a laptop.
No,
this is
essentially the idea is you need a big system with large amount of RAM and so on, which obviously are possible, but you need it. So in terms of portability of software, laptops won't be ideal for doing such large computation.
Yeah,
laptops
but in laptops, no. That's what I am telling. No, there I have a point here. Once this MicroSim tool gets developed, the post-processing tool gets developed for 3D, we can.
You can view 3D. What it does is it slices through the 3D file, and you can slice through a 3D structure and load the slices.
Oh, okay. So that is good enough. No, Saurav. That is good.
Yeah, you can load a 3D thing and you can slice through. You can choose the slice, go slice one by one, and look at it.
But those will be like 2D slices that will be projected.
Yeah, but you can essentially slice any number of times.
Okay. I understand. No, that's actually very good. But I think that isosurface capability also after stitching the slice.
That also is there. So you take the slice and then you can.
Oh, okay. So I'm sorry. These must be recent developments. So
they're part of the release.
Okay. These are part of the release. Okay, fantastic. So we will do that then. So thanks a lot for listening. And if you have any questions, you can also email us, and we will be happy to help. I think my thing is frozen now.
Yeah, so as you see, there are the solver is now capable, the entire set of solvers that you have capability to run the same int file on both CPU and GPU, as we have already shown in the overview. So that capability is now realized. Good, Sharmato, then we will take a tea break. And,
yeah. Okay, you take a tea break. Yeah. So anyway, it was really good. I missed you guys. I could not come. So because of some reason. And
yeah, hope your computer recovers.
Yeah. Now it quitted. I have tortured it enough. It gave up on me. Okay then. Yeah. See you guys. Yeah. See you. Bye. Yeah.
The next section will be the open form directly, because we already had a brief, nice overview of the post-processing tools in each of the sections. So we directly jump to the open form part of it. Yeah, to the participants also, can you tell Sauav?
Yeah.
Okay then. I am.
Yeah, see you after.
Yeah. Okay then.